And we're back. Okay, so think back all the way back to the first semester. You know, this is a crazy thought. Think about this. We are around 3/4 of the way through this course, just about, maybe a little less. Okay? If you were taking this at a traditional college campus, it would be just before Thanksgiving. Think about that. If you were taking this at a traditional college campus, you would only have one semester to get all this material done. And so in the course of we would be just before Thanksgiving. Get all this material. That's crazy to me. Get all this material done in one semester. But, I had to do it. Yes. Just go a lot faster, I guess. A lot less work time. Right? All right. Now, in the first semester, we had, within chapter 3, a section called Related Rates. Remember that section where I was like, okay, how fast is the balloon expanding if we're filling it with air with a certain amount of time, right? And we found the derivatives with respect to other pieces, and sometimes we had to do like implicit differentiation and so forth, right? Today's kind of like the same thing. A lot of word problems. Like all of the assignments is word problems. And the hard part about that is they're all different from each other, right? It's not like I can give you one cookie cutter way to do all of these problems the exact same way. I can't do that for you guys. You need to have intuition. You need to know, think about all the things that we've learned with respect to derivatives, and then apply all of those to the situation. And sometimes you'll do that and be like, oh, that didn't work. I got to do something else. And that's okay. That may happen. That may happen from time to time. Just don't get frustrated by that. All right. So what we're going to be looking at today is called optimization. The methods we have learned in this chapter for finding extreme values have practical applications in a lot of areas. A business person wants to maximize cost and they want to maximize cost. They want to minimize costs and maximize profits. A traveler wants to minimize transportation time. Fermat's principle in optics states that the light follows the path that takes the least amount of time, minimizing time. In this section, we solve such problems such as maximizing areas, volumes, maximizing profits, minimizing distances, minimizing time, minimizing costs. Find the smallest or biggest amount of things. Now, we've been doing that all along in chapter 4. Finding the biggest or smallest amount of something is finding the maximum or minimum value, right? If you can model a function based on a real-world situation, whether that be a function that's, quadratic or cubic or logarithmic or whatever it may be, if you truly wanted to maximize something, truly wanted to make it the biggest it possibly could, what you're going to do is find that maximum point. And we have a really slick way of finding a maximum point or a minimum point. You find the derivative, and then you can find then you're going to know where the zeros of the derivative are. Those are going to be your maximum or minimum point. In solving such practical problems, the greatest challenge is often how to convert the word problem into mathematical optimization problem by setting up the function that is to be maximized or minimized. We know how to do math. We know how to do this stuff in terms of just strict crunching the numbers. The difficult part is the application. The difficult part is taking what we know from the words and turning it into math. And I'm not telling you guys anything new. All right. Now, these are the problem-solving strategies that we talked about before. Remember, read the problem. But I just kind of want to talk through these because, again, this is a good route to take for all of these. First thing, understand the problem. The first step is to read the problem very carefully until it's clearly understood. Ask yourself, what is the unknown? What is the known? What is the given quantities? What are the given conditions? Figure out what you know and figure out what you don't know and write that out for yourself as well. Write it out. Second thing, and I do this a lot. Sometimes it's not possible. Sometimes the problems are a little bit more theoretical. But the next thing would be to draw out a diagram. In most problems, it is very useful to draw a diagram and identify the given and required quantities within the diagram. Third thing here, introduce some type of notation. Assign symbol to the quantity that is to be maximized or minimized. You call it Q, whatever. Select symbols that apply directly to what you have. Label the diagram as such. It may be helpful to use initials as suggestive symbols. For example, A for area, H for height, T for time. It's like, okay, come on now. We're not in sixth grade. Okay, express Q in terms of some other symbols, right? What you want to do is identify the function that is to be maximized or minimized. Consider that your like objective function. We did this kind of like in Algebra 2. We talked about they were called linear programming problems, where you graphed it all and you found your shaded region and you knew that the intersection points were the possibilities of maximize or minimize. Here, they're not going to be straight line functions; they're curves. So we're going to take that function that we want to maximize or minimize and try to express it just singularly in terms of other variables. If Q has been expressed as a function of more than one variable, use the given information to find relationships among those variables. Like for example, if we get a function and it's got X and R and A and B and C in it, that would be very difficult to find the derivative of, because you're gonna run yourself into implicit differentiation, because you're going to want to differentiate with respect to one variable, but you've got some other variable that's working that it's not a constant. You can't just take the derivative as a constant; it's going to change. So therefore, you're going to use implicit differentiation, and that is not the best route to take usually. It is a route to take. There's a time and a place, but usually it's not the best route to take. So what you want to do is figure out your way around it. Remember, we would draw right triangles. We would figure out some other relationship that we could put into that function so that we can make it all out of one variable, and then use those equations to eliminate all but one of the variables in the expression. Thus, Q will be expressed as one variable. Lastly, step 6, use the methods from sections 4.1 to 4.3, finding the absolute maximum or minimum values of the function, and by doing so using calculus. Now, we could do that in a couple different ways, right? Finding the absolute maximum or minimum value would either find the critical points and then run the ID test, or you could find the critical points and then the second derivative. Am I going to be asking you increasing and decreasing for all these functions? No, I'm not going to ask you that in these. But what I am going to ask you is identify a maximum or minimum value. Well, if the second derivative is very easily calculated, run it through the second derivative test. Remember, that is, if you got the second derivative, you plug in a critical point. If it's positive, critical point is positive, that means concave upward, minimum point. If it's negative, it's concave downward, that's maximum point. So you could use either your ID test or your second derivative test, depending upon the situation. And then don't forget that way back in section 4.1, we had this closed interval method, which is actually going to come up a lot here, because in real world problems, we're going to have certain parameters. We're going to have a low end and high end. We're only going to be looking at a boundary line of things, and that's the closed interval method. Okay, so we can use the closed interval method, the ID test, the second derivative test, all to solve these problems. All right, enough of me talking. Let's just do something. The rest of the lesson is just me doing problems. So I'm just going to tell you right now, you can start your homework tonight. Which I feel like I should take a side note and say that. Like, a lot of people are like, oh, there's so much homework. I can't do this. Okay, you can be starting your homework problems from the very beginning of the lesson, right? Like today, for every single lesson that we've done, the beginning homework problems are probably the first couple problems that we're doing on the notes. So don't wait until the last minute to do your homework problems. Now, for this particular section, I'm going to be giving you a lot of work time, but for the future, stop complaining that there's so much homework. Split it up over some nights. Don't wait till the last minute. All right, off my soapbox. Example 1. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a river. We're going to assume that that river is straight, doesn't bend. He needs no fence along that river. What are the dimensions of the field that has the largest area? So the first thing that I like to do is figure out the function that needs to be maximized or minimized. What do I need to maximize here? What do I need to maximize? The area, right? So I always make note to myself and say, okay, I want to maximize area, right? That's what I want to do. Sometimes that is a very difficult task to figure out what am I doing here? What am I trying to maximize or minimize? Now, I know the area formula, if it's a rectangular field, is just length times width. Let's call that x times y. Now, if I go to straight up find the derivative right now without any context, I'm going to have to use different, I'm finding the derivative with respect to x, and there's also a y in the equation. So that would mean I would have to use implicit differentiation. But maybe there's some way I could solve for x within y. Here's what I mean. Okay, so we got this river. Let's draw in our fencing that we have. Okay. If I call this dimension x, what is this dimension down here? X. So therefore, that would be y. We're told one other useful piece of information, that the fact that I have 2,400 feet of fencing. What's another equation that I could come up with x and y? What else could I come up with? Not x squared times y. X plus y is equal to 2,400. X plus y is equal to 2,400. Right? The perimeter, basically, without the river, 2x plus y is 2,400. All right, so solve for y. It's pretty easy. Y is equal to 2,400. That's a weird looking 2. 2,400 minus 2x. Okay, so now let's go back to our original equation and say, well, okay, so in that case, area is going to be equal to x times, use substitution here. I know that y is 2,400 minus 2x. Distribute the x. 2,400 x minus 2x squared. Now that gives me a function for area that only has one variable. That's the goal. You want to get yourself an equation that you want to maximize or minimize that only has one variable on the right side. Because how do I find the maximum amount of area? Well, I could take the derivative of the area function, right? That's going to give me the highest or lowest my area could possibly get. So let's find the derivative. Let's find a prime. Okay, that's 2,400 minus 4x. Okay, so therefore I know that if I find the zeros of that thing, that's going to be my maximum or minimum value. 2,400 minus 4x equals 0. Add the 4x. Divide by 4. 600 is equal to x. I know that's going to be my critical value. Do I know yet if that critical value is a maximum or minimum point? No, I mean, logic tells me that it's my maximum, but I don't know necessarily for sure yet. Okay, so here's what I would do, because we're gonna get deep into problems, and it's gonna be like, I don't know whether that's a maximum or minimum. You might have 2, 3, 4 critical points, and then you have to figure out what maximums and minimums there are, and then be able to tell what's the highest or lowest based off of that. Well, isn't this? This is a real world problem here that has real world parameters, right? What's my domain of my area? Like, what's my domain of my area? What's the smallest area I could possibly get? 0, right? What's my biggest area? Oh, I'm sorry. I'm not looking at area. Domain is X. Durr. What's the smallest X value I could possibly get? 0. Okay. What's the biggest X value I could possibly get? What if I use all of my area, or what if I use all my fencing for X and Y is 0? What's my X? Well, 2,400, right? But I've got 2 of them to split up. 1,200. Right? I guess I could put equal signs in here. Oh, this is the closed interval method, isn't it? Isn't this a closed interval? I've got a closed interval from 0 to 1,200, and I've got a critical point within that domain, right? Okay, so then let's just make a table. Let's make a table of values. Now, do I realistically think that 0 or 1,200 is going to maximize my function? No, but you would be surprised how many times that doing nothing of one and all of the other is actually going to maximize something. So we're going to find 0, 1,200, and then 600. And what are we going to do out of this? We're finding the area, right? We're finding the area. So let's plug it back into my original. Now, my original, watch out. I go X times Y. I don't know my Y values here. So just go back into the equation that doesn't have a Y value. All right. So it's 2,400. Well, if it's 0, it's 0. Right. Here we go. And if I, excuse me. Come on, buddy. And if I go 1,200, that's going to be 2,400 times 1,200 minus 2 times 1,200 squared. 0. Which makes sense. I mean, right? If my X value is 1,200, what would my Y value be? 0. 1,200 times 0, 0. So it's got to be 600 in there. I'm giving you a really simple example to start out with to show you how this is going to work. 2,400 times 600. And again, I'm going back into my original A, the reduced one here, minus 2 times 600 squared. 720,000. So that's my area, right? So obviously, the X value of 600 is going to maximize my area. Well, what was the question that was posed? What are the dimensions? Not just what is my X value, but what are my dimensions? All right, so if I know my dimensions, my dimension for X is 600. Well, what's my dimension for Y then? 2,400 minus 2 times 600. Well, 2,400 minus 1,200 is 1,200. So I know my X value is 600, where my Y value is 1,200. Those are my dimensions. Feet. To maximize area, I would need to build a 600 by 1,200 foot fence. Process. Again, let's kind of walk through the process again. First thing, define the function that you're trying to maximize or minimize. Second thing, create that function with one variable using the context that you were given. Something about the context is going to lead you to only having to being able to substitute back into that function to make it only have one variable. Next thing, to actually find the maximum or minimum point, find the derivative, and then find the zeros of the derivative. That's going to get you the critical point. Then, with all your critical points, figure out, okay, do I have a closed interval? What are my parameters for my x value? Then you can plug that in either using the closed interval method or increase-decrease test. If it's strictly theoretical, because some of them are. If it's just mainly, if there's no real world application to it, well, then you might have to do increase-decrease test or second derivative test to find that as well. But we use this the closed interval method, so we know 600, 1200 is my biggest. All right, take a look at another one. I'll plug in my computer. All right, a cylindrical can is made to hold 1 liter of oil. I know that my can needs to hold 1 liter. Find the dimensions that will minimize the cost of the metal to manufacture the can. I mean, how real world application are we going to get here? Okay, you're a business person. You want to minimize costs. You know you want it to hold 1 liter. I know I want it to be cylinder. What are the dimensions that's going to minimize costs for me? Now, what in turn is going to minimize costs? If I want to truly minimize costs, what do I have to actually minimize out of the can? The material, right? And if I want to minimize the material made, what truly do I have to minimize about the cylinder? The surface area. So I'm going to minimize surface area. Oops, I forgot my R. Surface area. Surface area. Now, what is the equation of surface area of a cylinder? Well, surface area is, think about top and bottom. There's two circles, 2 pi r squareds, plus an additional rectangle around the outside, right? Which the length of that rectangle is the circumference, 2 pi r, and the height of that rectangle is my h. So 2 pi r squared plus 2 pi r h. All right. So in the end, I'm going to need to find the derivative of the surface area formula. Issue. My radius and my height can change, right? Those things both could change. So I needed to figure out some way to get rid of either radius or height. Follow me there? So I know right off the bat, like I got to get a way to eliminate radius or height. All right. The only other piece of information I have here is that the can hold 1 liter of oil. Does anybody know? And I actually did not know this. I had to look this up. In terms of area, in terms of linear area, what 1 liter is actually equivalent to? How many cubic centimeters? I did not know this. 1 liter is actually equal to 1,000 cubic centimeters. I did not know that. I had to look up that. 1 liter is actually equivalent to 1,000 cubic centimeters. But that's talking about volume, right? A liter is talking about volume of the cylinder. Okay, so if I'm thinking about the volume of a cylinder, volume of a cylinder is pi r squared h, right? Area of the base times the height, pi r squared h. Okay, well, if the volume, what do I know the volume needs to be? 1,000 cubic centimeters. I know this volume needs to be 1,000 cubic centimeters. Do I have an equation that I could solve for either r or h with? Yeah. What's the easier route to take? Solving for r or solving for h? Solving for h. Could I solve for r? Yeah, but then what would I have to do in the very last step? Square root. Ooh, no thank you. Let's just divide over the pi r squared. So 1,000 divided by pi r squared is going to be equal to h. See, there are easier routes to take and there are more difficult routes to take. Choose the easier path. Okay, so that means I can plug this in. 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Okay, let's reduce that a little bit. So surface area is going to be equal to 2 pi r squared plus, okay, the pi's are going to cancel. This radius is going to cancel out with one of my exponents for my r. So 2,000 divided by r. Or in other words, 2 pi r squared plus 2,000 r to the negative first. Because again, when we're working with functions and I don't want to take the derivative, with polynomials, way easier than trying to think about it as a quotient. Okay, do I have an equation that I want to minimize that only contains one variable? Sweet, pi is not a variable, right? Okay. Pi is a constant. So we find the derivative, SA prime, the derivative of surface area. So that's going to give me, excuse me, 4 pi r minus 2,000 r to the negative second. Okay, so now what I want to do is reduce this down a little bit. Okay, so that's going to be equivalent to 4 pi r minus 2,000 over r to the positive second. Let's get a common denominator. Yeah, let's go r to the second here, which would bump that up to r to the third. I just multiply the left side by r squared over r squared. So that's going to get me 4 pi r cubed minus 2,000 divided by r squared. That's my derivative. That's my derivative. Okay, well, in this case, if I want to find the possibilities of maximum or minimum points, I need to not only find the zeros of this function, but I also need to think about when the derivative does not exist. When does the derivative not exist? When r equals 0. Okay, so here are my critical points. When r equals 0, and also when 4 pi r cubed minus 2,000 is equal to 0. Okay, add the 2,000 divided by 4 pi. It's going to give me a decimal here. 2,000 divided by 4 divided by pi. So 500 over pi. 159.15. And I'm going to cube root that. Cube root that. Oops, don't put math. Cube root of my answer. 5.42. Cool. Now, I could figure out my lower boundary to my radius. What's the smallest radius I could possibly have? I'm thinking about using the closed interval method. Like, is there some sort of boundary? What's my smallest smallest radius I could possibly have? 0, right? Wouldn't make sense to, I mean, that would really minimize cost. But that's the smallest radius I could possibly have. Can I define what the biggest radius I could possibly have is really easily? Not like I could with my rectangle, right? So maybe it might be better to run the increase-decrease test here to see if 5.42 was a true maximum or a minimum. All right, so r equals 0 and r equals 5.42. Now, do I care about what's happening to the left of 0? No, it's not within my domain. So let's see what's going on here and here. Let's plug in 1 to my derivative. If I plugged in 1, this would get me 4 pi minus 2,000, so negative, divided by a positive, so negative. Something bigger than 5.42. Let's say 6. 4 times pi times 6 cubed minus 2,000 positive 714 divided by positive 36 would get me something positive. Negative to positive. Oh, what is 5.42? Minimum or maximum? It's a minimum, which is exactly what we wanted, right? Now, oops, let's put this in blue. Put this in blue. Minimum at R equals 5.42. How do I know that there could not be another minimum? How do I know that 5.42 is going to be the only minimum that I have here? Does it have another turning point? No, because those were the only zeros of my derivative. So I know that this is going to continue upward on the right side and only keep going upward. It's not going to downturn again because there is no other maximum point, right? The only possibilities were 0 and 5.42. Follow me there? And anything to the left of 0, I don't care about. The only thing I care about is here, the positives. So I know the minimum value is when radius is equal to 5.42. All right. So let's figure out what the other dimension was, because I need to not only just find the radius, but also find the height as well. Well, let's plug it right into here. 1,000. One more zero. Pi times radius 5.42 squared. This is going to be my height. I did times. I was like, that is a giant number. There we go. Insert a divided by. Well, there we go. That is a little bit more reasonable. 10.84. 10.84. So my radius is 5.42. My height is 10.84 centimeters. You want to minimize costs? Make a can with those dimensions. It'll still hold a liter, and that will be the smallest surface area that you could possibly get, which will minimize costs. Sound good? Cool. We'll pick up there tomorrow.